Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on October 8, 2025, just yesterday. The striking result is that even top models follow multiple coding instructions poorly, with task success topping out at 46.75% on BigVibeBench and 40.95% on LiveVibeBench, while a combined score of instruction following and functionality best matches human preference. The paper is titled Vibe Checker, Aligning Code Evaluation with Human Preference, and the implications for model training are quite significant. In short, this paper introduces VeriCode with 30 verifiable instructions, builds Vibe Checker across 2 benchmarks, shows measurable functional regression under constraints, maps position biases, and finds single-turn prompts preserve functionality while multi-turn edits improve instruction following. So Figure 1 illustrates the core idea. A vibe check values instruction following as much as passing tests. The left panel depicts a user asking for Fibonacci code with a for loop, which is a specific instruction about style. The center panel shows a recursive solution that works, but fails the instruction, so it does not pass the vibe check. The right panel presents an iterative version that meets tests and follows the instruction. This contrast motivates verifiable instruction checks. Alright, Table 1 shows how the taxonomy turns real coding preferences into concrete, checkable rules. Each row pairs an instruction with a verifier, which is an automated test that returns pass or fail, plus any parameters. The examples span style limits like line length, logic caps like maximum branches, and documentation conventions. It also enforces safer patterns, like using the canonical OS error and switching file paths to pathlib, so constraints remain objective and scalable. So Figure 2 shows the evaluation protocol that contrasts single-turn generation with multi-turn editing. The left panel bundles all instructions into one prompt, so the model returns one implementation that tries to satisfy every constraint. The right panel staggers constraints across turns, which reflects real chat use, but risks more functional regression because code gets repeatedly edited. At the bottom, the metrics split performance into functionality, tested by unit tests, and instruction following, which means satisfying verifiable non-functional rules like style or documentation. Both settings are scored on the same axes, so differences trace back to interaction style rather than task content. Well, Figure 3 shows how constraints change outcomes. The left panels report functional regression, which means previously passing tests start failing as instructions accumulate. The curves climb steadily with more instructions, and single-turn prompts keep the rise smaller than multi-turn edits. The right panels track instruction following, and those lines fall sharply as constraints stack up. Multi-turn editing scores higher on instruction following, but it does so while sacrificing more functionality. So, Figure 5 shows that human preference aligns best with a balanced score that mixes instruction following and functionality. In the left panels for real-world programming, the Pearson curve peaks when the score weights about 40% instruction following. The Spearman curve there prefers around 70% instruction following. In the right panels for algorithmic tasks, the best Pearson blend again lands near 40% instruction following. The corresponding Spearman optimum sits around 60%, which confirms that neither metric alone captures what people like. Wrapping up, 2 takeaways stand out. Instruction following is a core signal for human preference, and constraints create real trade-offs, with single-turn prompts preserving functionality while multi-turn edits improve instruction adherence. The broader implication is clear. Benchmarks and training should include verifiable instruction constraints. That is it for the AI Research Roundup. I am Alex. Thanks for listening.